So my name is Raphael Clifford. I'm from the University of Bristol. And over these next 3 hours or so, I will try and tell you some things that we've done in the areas of lower bound streaming problems, but also there are going to be increasing numbers of open problems and increasing levels of uncertainty as we go through the time. So if you like uncertainty and open problems, then hang on. By the time we get to the third hour, we'll have no idea what we're talking about at all. So it's going to be great. Right. So you've heard, I suppose, quite a lot about data structure problems. These are streaming problems, which are related to data structure problems, but there's sort of a slight twist on them. So this, in some sense, is the original streaming problem. I don't know if people who aren't from Britain, anyone who's not from Britain know what game they're playing here? So this is Christopher Robin. That's Winnie the Pooh, and that's Piglet. And they're playing a game called Pooh Sticks. And in this game, you stand on a bridge over a stream, and you look one way at the stream, and you drop a stick down into the stream, and then you rush to the other side of the bridge and look to see whose stick comes through first. And if you can see your stick has come through first, you're the winner. Otherwise, you're terribly humiliated and you have to play the game again. So in this game, there are no video replays. There's no, you can't go back and argue about it afterwards. You have to see the stick as soon as it arrives. So in some sense, this is the original real-time streaming pattern matching problem. And that's more or less what we're going to talk about. We imagine that there's some data coming through at some alarming rate, and we have to spot something about the data as soon as it happens. We can't wait until later on. We can't save the data and analyze it the day after. We have to see it as soon as it happens. And this streaming problem, as I suggest, is going to be slightly different from the classic data structure setting which we've had, although closely related. So in order to prove lower bounds, we need a computational model. Some of you will have been here to hear about the CellPro model. Some of you will already know about it, but just to fix ideas, and particularly the way we're going to talk about it, we're going to try and prove lower bounds in the CellPro model. So in the CellPro model, we imagine there's some abstract view of memory, which has cells that are written out. These are just cells of memory. And each cell is W bits in size. And there's some abstract CPU that does reads and writes to memory, but it doesn't remember anything between its reads and writes. Anything it wants to know, it has to read from memory, that it writes to memory. Okay. And our CPU is going to have infinite computational power, which requires infinite cooling, which I think is my best effort for infinite cooling there. So we're not going to worry about the time it takes to do the computation, just the number of reads and writes. So if the total time for a computation, for an operation or an algorithm is going to be the time to take the computation, as in the arithmetic, plus the times of reads and writes, then clearly if we can show a lower bound just for 1/2 of that, the reads and writes, we have a lower bound for the sum. The problem is that we don't know how to prove lower bounds on arithmetic, so we don't do that. We just prove lower bounds for 1/2 of this sum. That's what's going on, basically. So the whole thing can be done in the CellPro model. This is our lower bound, but the important thing to understand is that if you prove a lower bound in the CellPro model, you've certainly proved a lower bound for any sensible model of any sensible serial or sequential model of computation that you can think of. So these are real lower bounds for real things you should really be interested in. Right. So people have looked at, so far this week, data structure problems. So Casper gave a lovely introduction, and people have talked more from there. And classically, there are two types of data structure problems. There's what you might call static data structure problems. These are query-only problems. And these problems, you have some data which is stored, and you're not allowed to change the data, but you're allowed to make repeated queries to the data. That might call that type 1. In type 2, this is a very dynamic chap here, we have dynamic data structure problems. In this situation, you're allowed to update the data as well as query it. So the data doesn't remain static. This is a little child here who's suffering from a terrible problem of static. But our streaming problems, which I'm going to introduce in a moment, are in some sense type 3, or you might say type 2a, where we're only going to do updates. You might think, if you only do updates, how do you get an answer? Well, there will be a query, but it's always exactly the same query. There aren't different sorts of queries. So it's really a kind of quite extreme subcase of type 2, or you might call it type 3. So these are update-only data structure problems, and it makes a difference to the techniques or the way you have to think about it for lower bounds. Did you want to ask a question?
Yeah, okay, so that simply throw away everything, whatever comes in, this would be a fine thing. So that in this case, only update.
Yeah.
If you're not interested in anything whatsoever, then do nothing. So that's, you have to do some things and not only update. That's right.
So there will be a query, but it's always the same query. So crucially, in the techniques for proving lower bounds in the dynamic setting, we have many different sorts of queries, and that often takes a crucial part of the analysis. But in this case, there's going to be, and it'll become clear in a minute, there'll be only exactly one sort of query. So the only thing that varies of any interest is the updates. So here's a sort of brief potted history of, well, old history of data structure lower bounds, and it's just to give you, for those who are not familiar with the field, a picture of what's going on. So the cell probe model was probably invented by Minsky and Papert, but in the setting we're interested in, we'll say Yao in 78. And then 10 years afterwards, you'll see, there's big gaps. There were a number of lower bounds for static data structure problems were proved by Itai, Milton, Beam, Fitch, and others. It wasn't until 89 that the chronogram technique of Fredman and Sachs was invented. This was a technique for proving lower bounds for dynamic data structure problems. And we'll see here a collection of results from 89 until 2000 and something. The point about listing these on the screen is just to give you an indication that the results don't come thick and fast. Although this isn't all of the results between 78 and 2001, it's, let's say, a good constant factor approximation of the results. It's, even though you have a technique, to actually use it for a specific problem is non-trivial. So up here we have the classic static data structure problem of predecessor search. So we have some set of numbers, let's say. We have a query x, and we have to return the largest number that's smaller than x, or no greater than x. Okay, that's the predecessor search problem. Down here, the classic problem is the partial sums problem. So dynamic data structure here, we have some array A, and we're given an index and a value to update it with, and we add that value to the ith element of the array A, and then a query asks for the sum of the first k elements. So notice we have updates, we give an index and a value, and we have a query that has a k. So there are many different sorts of queries. Right? Okay. And the chronogram technique only allows us to prove lower bounds of form log over log log, as we discussed earlier in the week. That's all you can do. There's nothing better you can do strictly using the chronogram technique. And then in 2004, Mihai Petrescu and Eric Demain, Mihai Petrescu has been mentioned a lot in every workshop I go to, and so he should be, quite a remarkable genius, showed a new technique which he called the information transfer technique, which allows us to show log lower bounds. So some of these problems have log upper bounds as well. So this gives tight results, but also the technique is rather beautiful, is rather simple, and is the crucial one which we're going to use for basically the whole rest of this tutorial. It's going to be the information transfer technique. After 2004, for other problems that don't have log upper bounds, Casper here shows that we can sometimes improve the lower bounds to something like log squared. However, our problems that we'll discuss have log upper bounds in the cell probe model, so that techniques won't be relevant to us, unfortunately. Right. So let's recap. Our string problems, which I'm going to define in a moment, are going to be update only. They're going to be type 3, but in particular, they're going to be even worse than update only, where an update normally has, well, in the example I gave you, had an index and a value. Our updates are only going to have a value. It won't even have an index. It's just a number is going to arrive. And that will also make a difference at some point later on, that I will discuss to you. So let's tell you a specific problem. So here's a specific streaming problem. Right. We want to multiply two numbers. We're going to multiply them in the stream. So what's going to happen, we're going to have digits for some set, and pairs of digits are going to arrive at a time. So the first, and they arrive from the least significant digit first. So if a 2 and a 3 arrive, then I can immediately tell you that the product of 2 and 3 is, and I almost felt like asking you the answer, but I think we'll work it out. I may ask you questions later on. Is 6. So that's great. And then a new digit comes in, 4 and 8. And we know that whatever happens in the future, we're able to output this digit here. So we know that the next digit is going to be an 8. And every time... is that right?
No.
Why not?
8 is 32.
No, but we're multiplying... So these are two numbers we're multiplying together. So this is 42 times 83, currently.
Oh, 42 times...
83. What is 42 times 83? Do you want to do it in the head? You needed to add 6 to 2 was the point to get 8. Okay? Okay? Okay. So we get another pair of digits in, and it's almost an alarming arithmetic problem there. Another pair of digits. Every time we get a new pair of digits in, we know we can output one new digit of whatever the product will be ultimately. Right? We don't know the future digits yet, but we know this digit for sure. Okay? So every pair of digits tells us exactly one new digit for sure of the product. Okay? So we carry on doing that. And if we want to know the rest of the digits, then what we'd have to do is read in lots of zeros, and then we could then each time we got a new zero in, pair of zeros in, we get a new digit of the product, and eventually we know the product of 52640142 is and 710429983 happens to be that long number. Okay? Right. So it's a streaming problem. We get a pair of digits at a time. Each time we get a pair of digits in, we have to output one new digit of the product. So the question we're asking is, how long does it take? How quickly can we output one new digit of the product? That's the problem we're trying to solve. So is that question, is that sort of the setup of the problem clear? Okay. Right. So what we will show is that you must take over n of these operations at least n log n times delta over w time. And delta is going to be the number of bits needed to represent a digit. And w, remember, is the size of the word in our computational model. So historically, this problem has been looked at before. So Mike Patterson, Fisher, and Meyer in '74 looked at this problem. And they showed an n log n lower bound in the multi-tape Turing machine. He also showed, perhaps even more interestingly, an n log n over log n lower bound in what's called the band activity model, a perfectly sensible model of computation that went completely out of fashion. And so in some sense, what we've done, we've modernized it. We've looked at the computational model of modern interest, and we've shown sort of a similar-ish result. Right, here's the second problem. The second problem is the problem of cross-correlation, which I have eventually conceded to call convolution, but more properly as cross-correlation. And here we have a fixed vector, v, and we have a stream of numbers, integers, let's say, that come in one after another. And every time a symbol comes in, we have to output the inner product between v and the n-length suffix of the stream. So in this case, it will be the inner product between v and x0 to x7. A new symbol comes in with the inner product between v and x1 to x8. Then the inner product between v and x2 to x9, and so on and so forth. And the question here is, how long does it take us to produce this new inner product? Now, naively, of course, you could just compute the inner product. It would take n time if vector is length n. So we show a lower bound that it must take at least log n, where n is length of v, times delta over w. Well, delta here again is the number of bits needed to represent one of the integers that comes in, and w is the word size. So log n is a long way from n, but I'll try and persuade you in a moment that it's not so bad. And the overall proof technique we're going to use really for all our methods, it relies crucially on Yau's minimum principle. So we're going to try and construct random input distributions for which we're going to show a lower bound for any deterministic algorithm. That's actually what we're going to do. But of course, it's not what you want. What you want is to know that there's a lower bound for any randomized algorithm on any worst case input. And Yau's minimax is going to take us from what we actually do to what we want. And of course, any lower bound for any randomized algorithm is a lower bound for any deterministic algorithm, for those who worry about those sort of things. Okay, so we have these log lower bounds, but are they any good? What's the upper bound, you might ask? Well, Fisher and Stockmeyer, and also myself and Fomenko Part looked at upper bounds for these problems. And so this was specifically for integer multiplication. What we did later on is we gave a general online to offline reduction, which says for a large class of problems that you want to solve online, by online I mean you want guaranteed worst case time complexity for every new symbol that comes in. One symbol comes in, you must give an output. Another symbol comes in, you must give an output. You want a guaranteed worst case time complexity. How long is it going to take you to give an output? And our general method, you take the offline time complexity of the problem, divide it by n and multiply by log. That's the formula. So in particular, this problem of inner product, cross-correlation, of course, you can solve using fast Fourier transforms. Offline, n log n time, divide by n, multiply by log, you get log squared time. Multiplication, fast Fourier transforms again, n log n time, divide by n, multiply by log. So we get log squared time per arriving symbol. So we have this lower bound that looks like log, this upper bound that looks like log squared. Okay? So you might again say, well, why don't you make them tight? What's wrong with you? There are two issues. One of which is that, remember, we have this general online to offline reduction. Now, it's true that in the RAM model, in the sensible model of computation, these algorithms offline take n log n time. But in the CellPro model, which is not a model that should ever be shown an offline problem, but were you for some reason to show this CellPro model an offline problem, it just reads in the input and gives you the output. Computation is free. So in the CellPro model, offline, this stuff is linear time. Everything's linear time, basically. You just read it in. Which means using our reduction, there's an online upper bound in the CellPro model of log n time. So in fact, our lower bounds cannot be improved in the CellPro model because the lower bound hits the upper bound. Okay? So in the CellPro model, they're actually tight. So you might say to me, there's something wrong with your CellPro model. Find me a better model and prove me a better lower bound. But there's a problem with that as well, which is that using our online to offline reduction, exactly the same piece of reasoning, any lower bound for these problems that was higher than log in any computational model that you want to think of would imply a superlinear lower bound for the offline time complexity of, for example, multiplication. And that would be a truly shocking result in complexity, I mean a wonderful result, but given that we don't have a superlinear lower bound, for example, for SAT, it seems odd to start with multiplication. So that seems tricky to do. So maybe you can improve the upper bound of log squared. First open problem, don't know how to do it. There are a number of open problems, that's number one. If someone wants to count them, that'd be great. Right, so we're going to use these information. So let's try and actually dig into it and show you how these techniques work. Yes?
Can you say a little bit about that last connection? So you're saying an algorithm for multiplication would give you
Oh, so this one here. Yeah, I'm saying if you could prove a lower bound above log for online multiplication, that would give you an offline lower bound above linear.
Yeah, so the question is, can you say more about that? Why is that true?
Oh, why? Oh, because of this reduction up here, which the formula is that you take the offline complexity divided by n and multiply it by log, right? So this reduction here immediately implies that. Okay, yeah.
Do you have any space limitations?
No space limitations in this work at all. Yeah. Yeah. It would be interesting to introduce space limitations. Yeah. I think Caspar has some work with CellPro model and space limitations, is that right? Yeah. Yeah, that would definitely an interesting area, definitely a good area. Yes, there's a huge number of I like to think there's a kind of a wilderness out there, and we've taken one particular little path through it. And if you ask me what happens in the forest, the left and right, I don't think I really know at this point. Right. So let's try and dig into it and actually give you a complete proof using information transfer techniques so we get a feeling of what's going on. Let's try and see if we can squeeze that into the first hour or so. Right. Right. So the information transfer technique. So it's been introduced by Casper, but we have a slightly different way of looking at it to fit our streaming setup. It's the same thing, just looked at from a different angle. Right, so how do we look at it? So this is the stream that comes in, and this is our fixed vector. Let's say we look at the cross-correlation problem, these are inner products. And these are memory cells. We imagine that symbols are coming in, and for the moment, let's assume these are all fixed and known, so nothing interesting is going on at all in the stream. Okay. So symbols come in, and eventually we have a symbol comes in that we don't know. And every time a symbol comes in, of course, you have to output an inner product. So when this symbol comes in particular, we have to output an inner product. In order to do this computation, we're going to have to read and write some stuff from memory. So let's say when this comes in, we happen to write to this place in memory. Right? When that symbol comes in. Next symbol comes in, we happen to write to those two new memory cells. Another symbol comes in, we happen to write to another memory cell, and then another memory cell. Right. Okay. So let's say that's the unknown region. And then we have some things that are fixed and known. Of course, this comes in, we have to output something. And when we output something here, we have to read and write. We have to read from memory. And we just happen to read from this cell and this cell in order to give the output when that comes in, that symbol comes in. Another symbol comes in, and we happen to read from this cell. But in this cell, you notice, was written in the time period before. And we have another couple of symbols come in. And sometimes we read from cells that were written in the time period before, and sometimes we read from cells that were not written in the time period before. So the information transfer, it's defined to be those cells, memory cells, that were written in the time period before, read in this period, and not overwritten in between. And that's what we want to argue about. We want to argue about the size of the information transfer. Fundamentally, the fundamental proof technique is that if you can show the information transfer is large, then you can show a lower bound for how long it has to take you to do the computation, because you have to read stuff. That's basically what's going to happen. Right. And first thing we have to persuade ourselves is that the only thing we need to know about this region here in order to output the correct outputs here is information is the data in information transfer. Everything we need to know about this region in order to give these answers correctly is in these cells that were written in this period, read in this period, and not overwritten in between. That's all we need to know about it. And what we're going to show is basically two inequalities. We're going to first of all argue that the entropy of the outputs during this period, given all this fixed stuff is fixed, is going to be upper bounded, it's a new verb, by the expected size of the information transfer multiplied by the word size plus the word size, but the key point is that it's going to be upper bounded by some function of the expected size of the information transfer. And then later on we're going to show a lower bound for the entropy, and this is going to give us a lower bound for the size of the information transfer. That's what the game's going to be. So first of all, let's try and persuade us this information transfer is actually the right thing, and try and actually see how do we get this inequality here. So the entropy of any random variable is always less than or equal to the size of any encoding of that random variable. Right? So basic information theoretic fact. So we give an explicit encoding. And here's an explicit encoding. For the information transfer, we simply store the address of every cell that was written, and not overwritten, and so every cell that was in the information transfer, and we store its contents. And it takes us W bits to store the address and W bits to store the contents. It's very simple encoding. We also need another W bits, I think, in order to make sure we know how long this encoding is going to be. And the way we use, right, so that's the encoding. We have to persuade ourselves then that we can actually use this encoding. And so the way we use this encoding is we simulate some algorithm that's running along the input here, and then stops just before the unknown region. and then skips over to here, doesn't read any of the unknown region, and carries on, and only uses the information transfer. And what's it do? Well, every time it does a read from memory, it looks at the address and says, is that address in the information transfer? If it is, it just reads the contents from the information transfer. And every time it does a write, it checks, is the address I'm going to write in the information transfer? If it is, it zeroes out the thing in the information transfer and then writes to memory. So this is how you use it, and so hopefully this will convince you that it is actually sufficient in order to do what we need to have done. So that's the lower bound for the information transfer. But how much about this information do we actually need? Right. Sorry, in order to give the correct outputs. Well, it depends, crucially, on what this vector here is. There are some vectors for which we don't need any information at all about the unknown region. So this is my first question to the crowd. Who could, sorry? All zero, thank you very much. So the all zero vector, we don't need to know anything at all about this unknown region. There are some vectors for which we need to know something, but not much. And it's worth looking at the all one vector. The problem with the all one vector is that we don't need any new information about this region for every new symbol that we read in. So we need delta bits, but then it's the same delta bits for everything new that we read in. So what we need is to construct some vector for which we need to learn a lot about the unknown region in order to give these 4 outputs that can happen after it. So this is such a vector. What we do is we put 1s at power of 2 positions, starting at the least significant bit, going this way, and have exactly the property that we want. So let's imagine the unknown region is of length L, the period after is of length L, and we read in symbols. So let's make L a bit bigger so the picture looks prettier. So at this point we give some output. Let's not worry about why or how at the moment, but let's just imagine a new symbol comes in, we give some other output, new symbol comes in, another output, we see it sliding along. And then after L over 2 new outputs, we'll notice this happens. What happens here is that only one of the ones in this vector is aligned in the unknown region. And remember, we know all of this stuff. We know the vector, so we can, and it's just an inner product, right? So we can subtract off the contribution from everything outside the unknown region, which tells us precisely what the value is in the unknown region. The R stands for recovery, I think. And the next time a symbol comes in again, we know precisely what the next thing in the unknown region is. And the precisely again and precisely again. So we get to learn exactly half, well, at least exactly half, I suppose, but we certainly get to learn half of the symbols in the unknown region. Sorry.
So that you're going to learn more later. Oh, I see. No, but it's going to time out or something like that. But that's within the next group of the same size.
Yeah.
You're going to learn.
Yeah, exactly. Yes. Yeah.
So it's going to relatively soon you'll learn that.
Yes, that's right. You'll learn. That's right. And then eventually we're going to have lots of these regions of power of 2 length L. So this just for one particular fixed length L, we learn half of it. Of course, we may actually learn some more information entropy-wise than half, but at least half. So if L is a power of 2, then we recover L over 2 values exactly. And of course, this tells us immediately that the entropy, conditional entropy of these outputs, given all the stuff is fixed, has to be at least L over 2 times delta, where delta was the number of bits needed to represent a symbol. Because that's just the entropy of one symbol, and we get L over 2 of them, precisely. And this tells us now, just by solving the inequalities that we have now, because we have an upper and lower bound for the entropy, that the expected size information transfer is at least delta L over 4W, well, with some constant. Right. The key point is it looks like delta over W times L. So that's for one fixed region of length L. Now, the point is that actually we don't want to know the expected size. We don't want to know the conditional expectation. We want to just the expectation of the thing. But we solve that just by taking everything to be uniformly at random, and then by linear expectation, we find the expected size of information transfer is actually bounded below by this delta L over 4W. Okay. So that's all very nice there, but what do we do with it, you might ask me? Well, what we do with this thing is this rather nice, use a rather nice object called the information transfer tree. I'm not sure who invented it originally. I know Mihai used it. I think there are similar ideas in earlier papers by Mike Patterson. Anyway, we use a rather nice thing called the information transfer tree, because remember we have this result for one interval length, we want it to sum it up to give a result for our whole entire input. And what we do is we look at consecutive regions of power of 2 length again. So we imagine here we know now that we have to in order to give the answer here, we have to transfer some information about this region here, and we've argued about how much information that's going to be. In order to give these two answers here, we have to transfer some information about this region length too. So you can imagine the information going up the tree and down again. And again, we can look at every power of 2 length, consecutive power of 2 length intervals, and we know a lower bound for the amount of information that has to be transferred from the left interval to the right interval. And now what we want to do is we want to sum all these information transfers over the tree. Well, if you look at it very quickly and sort of don't think about it, you might worry that, hang on a second, you're counting the same thing more than once. But in fact, you're not. And there are many ways of saying that you're not, but perhaps I find the simplest way to think about it is just to draw any vertical line you choose from a node and look at the data going from the left to the right of it, and you will notice that there's no two sets of intervals left and right of it that transfer. Well, the information never gets transferred twice at the key point. So you sort of draw a vertical line, I know down here, for example, there's information going from there to there, and information going from here to here, but there isn't any other information going from that half to that half. So in fact, there's no double counting, which is a rather nice result. So you just sum over this tree. So if we just do the sum, this is the sum of the information transfer over all these nodes in this information transfer tree. We have the expectation of the sum is the sum of the expectation, and we know a lower bound from this, what we just talked about beforehand, which is this thing here. And if we do the summation, we find that over n inputs is a lower bound of n log n over delta w for the number of reads, actually. We can talk about writes, really, for the number of reads that you have to perform. So if we're interested in amortized results, this gives us an amortized time lower bound of delta over w times log n. So this is a complete proof. Hopefully no details missing. I think it may be the only complete proof you get in my tutorials. But I just want to give you an entire proof of a lower bound result using this information transfer technique. Does anyone have any questions about this? The one and only complete proof. Oh, they get less complete as time goes on. Okay. So this, I think, is very pretty and nice and simple, and I think sort of teachable to advanced undergraduates, because there's nothing complicated going on, particularly, once you've got your head around the concepts. Or maybe in teachable to advanced undergraduates, I just realized I should also say writable by advanced undergraduates, given Mihai Peșescu's result on this. But anyway, this area. Okay. So you might say to me, I mean, it depends what your hat on, but my hat, I always kind of like to think slightly practically. And you might say to me, well, it's all very good. You found me one fixed vector for which it's hard to perform, let's say, cross-correlation, but maybe that's the only one, and so who cares? You just found a really weird vector, right? And whoever wants to multiply that strange vector you've made up? But it turns out that's not the case. Let's just choose a vector at random, so rather than this particular fixed vector we had before, and let's look at see what happens. We want to persuade ourselves that lots of vectors are difficult to perform, are difficult for the cross-correlation problem, not just this one weird one I happen to have made. So let's actually have a look at it again. Let's revisit it. So we have this vector here, and every time a new symbol comes in, remember we have to put a new inner product, and we're going to just write out the parts of the vector involved in a product here as rows of this matrix. And we're going to look at this unknown region as it sort of looks like it's going to move to the left as every time a new symbol comes in. So we get a new symbol in, we do the inner product between V9 and V2 and X8 to X1, and this gives us some product Y7. A new symbol comes in. we now have v10 to v3 in the same inner product of that with the same vector x8 to x1 gives this new one. And every time a new sum comes in, we get a new inner product, right? It's just exactly the same as we had before. We're writing out in matrix form. So there it is. That's the calculation we want to do. And you'll notice this matrix is terplets. So the falling diagonals are constant, right? It's x10 down that diagonal, v10 down this diagonal, v9 down that one, v8 down that one, so v7 down, so on and so forth, right? Okay. So what we'd like to know is what happens if we choose one of these v's, right? At random, well, that's the same as choosing a random terplets matrix. And it turns out, because our operations can be, for our lower bound purposes, can be over a finite field, it turns out that if the Q is prime, and we operate over this finite field FQ, then a terplets matrix is likely to be invertible. Well, if it's invertible, then we recover all of these values here. Okay. So in which case, we get the same lower bound using a random vector v. Okay. Because with good probability, the thing is invertible, which gives us actually the whole of the unknown region. So it turns out that, in fact, lots of, and if Q is more than 2, most vectors V are hard to form computation, to form cross-correlational. It's quite satisfying. So this is a end of the theme, but I think I stopped too early. People will go crazy, so I won't do that. Right, so quickly on, move on to multiplication, that's right. Right. So we had cross-correlation and multiplication. I'll just cover multiplication quickly and give you a more or less complete proof. Well, not quite, more or less of what's going on. So if we remember, there exists a lower bound of n log n in the multi-tape Turing machine for multiplication problem and n log n over log n. Multiplication is an interesting problem to study because it turns out the Egyptians were interested in multiplication. This is the little picture of the bit of the Rhind papyrus, which I think was published in 1650-ish BC, or BCE, depending on your mood. And when writing papers, it's always attractive to say that you've tackled a 5-year open problem or a 10-year open problem, whatever it is. But the Egyptians were very interested in multiplication. They had a method of multiplication that looks a lot like multiplying by binary numbers. And so in some sense, one could say that we'd tackled and made some progress on a 3,500-year-old open problem, but I couldn't bring myself to write it in the abstract. I'll say it to you instead. And for this online multiplication problem, we have more or less the same low bound discussed before. So how does that work? Well, what we'd like to do, of course, is just use the same hard pattern we had before, but you have to be a bit careful about it. The symbols that come in a multiplication are not binary. So instead what we do is basically you just bit pack. So we're going to put the ones at power of 2 positions, but in some binary representation of the number which we're going to multiply by. Instead, so it looks a bit like this, for example, in, I guess I'm in hexadecimal. If I do that, the symbols come in as before, and we use this following fact, and the following fact says that for any fixed digits here and any outputs here, there can only be at most there are only two possible options of what's in here. It's just a mathematical fact. And this immediately gives us our conditional lower bound that we like to have. It tells us the entropy of the outputs, given all the fixed stuff is fixed, is at least something like delta L over 2, which is what we had before, but rather pleasingly we get the same thing for multiplication. And again, you might ask me, well, there's only one hard number to multiply by, that's not really a problem, is it? But it turns out that actually most numbers are hard to multiply by. So if we instead choose a random number to multiply by, then we end up with this slightly more subtle fact that says that for any of the fixed digits and any of these L outputs, for at least half of the possible values in this region here, there can be at most 4 possible outputs four possible values for what's in here. So basically, most numbers highly restrict what's in the unknown region. Okay. So those two mathematical facts were proved, I think, by Mike Patterson and his co-author in the 70s. So we just sort of copied those mathematical facts. Hi. Right. So I think I will stop there and for coffee break, so that it's a logical break. Okay. So coffee time.